Hello again, ladies and gentlemen. Today we are covering section 2.7. Again, we're proving things. This is proving angle pair relationships. And we talked about angle pair relationships back in section 1.5. Different relationships are angles being adjacent, complementary, supplementary, vertical angles we talked about, linear pairs, things like that. So we're going to be introduced to some theorems today for the first time and some postulates that we'll look at. The first thing is theorem 2.3, and theorems, unlike postulates, must be proven. So anything that is a theorem, there exists somewhere in geometry a proof for it, because Euclid, when he was forming his system of plane geometry, took some postulates and proved everything that we know. So theorem 2.3, the right angles congruence theorem, has a proof that Euclid wrote. And it simply states that all right angles are congruent. So again, there's a proof that shows that all right angles are indeed congruent. And we can use these theorems in proofs since they've already been proven to be true. So any theorems we go over are fair game to be used or required in a proof. So looking at a proof, we're given that these specific line segments, so segment AB and segment BC are perpendicular, segment DC and BC are perpendicular as well. We're looking to prove that angle B and angle C are congruent. Well, we know that if they're perpendicular, they should be right angles, and we're going to use that fact in our proof today. So we'll start with our given information, knowing that they are indeed perpendicular, because we'll have to use our given information at some point. So let's use it at the beginning and see if we can use it to build upon. Well, if they're perpendicular, then we know that angle B and angle C are right angles, because the definition of perpendicular lines says that they are two lines that intersect to form right angles. So therefore, angle B and angle C both must be right angles, because those are the intersections of these two pairs of perpendicular lines. And the theorem we just talked about says that all right angles are congruent. So we can say that angle B is congruent to angle C. And that's using our right angles congruence theorem, simply stating that all right angles are indeed congruent. So that's our proof, proving that angle B is congruent to angle C. Feel free to rewind and go back through it. And again, we already covered this in class, so if you have questions on it, please ask me in class as well. Two other theorems we're going to talk about are congruent supplement theorem and the congruent complement theorem. And we always try to name these theorems with their name, not their number. So if you're going back through a proof later on and you see theorem 2.4, you don't have to scratch your head and say, well, I don't remember what 2.4 was. If you use the congruent supplements theorem as the name, you have a better idea of what it's talking about. So this says if two angles are supplementary to the same angle, or to congruent angles, then they are congruent. So as an example, looking at the picture on the right, if angle 1 and angle 2 are supplementary, and angle 3 and angle 2 are supplementary, then angle 1 is congruent to angle 3. So two things I want to point out. One, let's do a concrete example. Let's say that angle 1 is 30 degrees. Well, looking at our first statement, if angle 1 and angle 2 are supplementary, knowing they should add to 180, then angle 2 must be 150 degrees. Looking at our second statement here, angle 3 and angle 2 are supplementary. So if angle 3 and angle 2 are supplementary, then they should add to 180, so angle 3 should be 30. And we can see that those two angles are indeed congruent, or equal. The measures are equal. So if they're both supplementary to the same angle, to angle 2, then they're congruent to each other. What some people like to look at this as is kind of a variant of the transitive property. You cut out what's the same and say that these two are congruent to each other. So it's similar to the transitive property, but it's not transitive because we're not using all equals, we're using supplementary, resulting in congruence. So that's congruent supplements theorem. Congruent complements theorem is exactly the same, but instead of supplementary angles, we're talking about complementary angles. They add to 90. So for our example over here, if angle 4 and angle 5 are complementary, and angle 6 and angle 5 are complementary, we can cut out what's the same and say these two should be congruent. Angle 4 is congruent to angle 6. And to throw some numbers in here, let's say that angle 4 is 30. And if you're using our first statement, angle 4 and angle 5 are complementary, they should add to 90, so angle 5 should be 60. And our second statement, if 6 and 5 are complementary, they should add to 90. So 60 plus angle 6 should equal 90, so angle 6 must be 30. So again, we're using a concrete example to illustrate our theorem 2.5, our congruent complements theorem. So let's look at a proof involving this. Prove the two angles supplementary to the same angle are congruent. So we're given that angle 1 and angle 2 are supplements, and angle 3 and angle 2 are supplements. We want to show that angle 1 is congruent to angle 3. So this is kind of a proof of the congruent supplements theorem. So our first reason obviously is given because it's our given information. And for step 2, we went from saying they're supplementary to saying they add to give us 180. We went from saying they're supplementary to adding to give us 180. And so our reason we can go from supplementary to 180 is because of our definition of supplementary angles. The definition says if they're supplements, they add to give you 180. So that's how we can go from step 1 to step 2. Now if they're both equal to 180, then they will be equal to each other. So the measure of angle 1 plus the measure of angle 2 equals the measure of angle 3 plus the measure of angle 2. They're both equal to 180, so we cut out what's the same, transitive property, and set them equal to each other. If you use substitution, that would also be fine. Substituting in angle 1 plus angle 2 for the 180 down here, plugging it in, that would be fine as well. What we're used to seeing with the transitive property is the second line, we're used to seeing it flipped, where the 180 makes it a diagonal. Now, we couldn't use it that way with the law of syllogism if it was in this form where they're on top of each other, but we can with geometry or algebra, because this is kind of like saying, if we're going to use algebra, if we set x equals 4 and y equals 4, we can logically say they're equal to each other using our transitive property. So again, the order doesn't matter so much when we're talking about the geometry or the algebra, but it did when we were talking about logic. So since they're equal to each other, my goal is to have angle 1 congruent to angle 3. Well, here I have some unneeded stuff. I have angle 2 on both sides that I don't need. So let's get rid of that angle 2 from both sides and just have angle 1 equals angle 3. And if we're subtracting it from both sides, that's our subtraction property of equality. But we're not quite finished yet because we're not asked to prove if the measures are equal, we asked to prove if they are congruent. So to go from the measures being equal to saying they're congruent, we use our definition of congruence, or in this case, definition of congruent angles. So making that switch from equals to congruence is essential. And obviously we know if their measures are equal, then they're congruent. And our reason would just be the definition of congruent angles. So that's kind of proving a case of the congruent supplements theorem. It's kind of something you might have seen Euclid write to prove that it's true. All right. So let's move on from congruent supplements. And let's look at some oldies but goodies. We talked about linear pairs in chapter 1. And we know that if two angles form a linear pair, they form this straight line and share a common side, kind of making that Y shape. And they're supplementary. Of course they're supplementary. They had to give us a straight angle, which is 180 degrees. But we use this in postulate form in our proofs because, remember, a postulate doesn't need any proof. It's something that's accepted as true, and Euclid wrote it as a postulate. So now that we already know the concept, we're going to use the specific name now in our proofs. Same thing with vertical angles from chapter 1. We know that all vertical angles are congruent. They are formed by that X shape when you have two lines intersecting. And all the angles across from each other are vertical angles, and they're congruent. And this is a theorem because there's a proof of it somewhere, possibly in your textbook or possibly elsewhere in another textbook or another sort of geometry book. And there's a proof somewhere we could look at to see why this is proven as true, how Euclid did this, but we're just going to accept it as a theorem because we know that it has already been proven. So now we can use Theorem 2.6, our vertical angles congruence theorem, and postulate 12, the linear pair postulate, in a proof. So we have more tools that we can use now. And we'll do one of those in just a moment, but let's do a quick review of some algebra with that. So we're just going to write an equation here. Which equation can be used to find x? We know we have an expression, 3x plus 1, that involves x. And we have a 32 degrees over here. Now, if we're looking at this angle pair relationship, they form this straight line together, and they share a common side. That makes them a linear pair. If they are a linear pair, then we know that they are supplementary. So we can write an equation, our 32 plus 3x plus 1 should equal 180 because they're supplementary. So that's going to be answer choice B. They're supplementary, not complementary, not equal, not vertical angles, and not this distractor. So we know it should be answer choice B. But we did a lot of problems like this in chapter 1, so this is just kind of a review setup problem because we've done tons of these before. So let's look at a proof involving this sort of stuff. So we're given that angle 2 is congruent to angle 3. And let me mark my diagram with that just so it's easier for me to visualize. They're congruent, so I put the same number of curves in each angle. And we're asked to prove that angle 1 is congruent to angle 4. Well, let's look at this logically before we do our proof. We know that these two are congruent, and these two are congruent because they're both vertical. So then 1 and 4 should also be congruent to each other, just like 2 and 3 are. So logically, it makes sense, and let's go through that as a proof. So again, we start with our given information. Angle 2 is congruent to angle 3, and our reason is given. Always a great start. And then whoever it was that filled out the statements for this proof said that angle 3 is congruent to angle 4. Well, that doesn't really make sense just looking at our given information, so let's take it to the picture, knowing that angle 3 and angle 4 are congruent. Well, of course they are because they're vertical angles. They're across from each other. So that's our vertical angles congruence theorem, which says that those two angles are congruent to each other. Now our third step says that angle 2 is congruent to angle 4. Well, that doesn't make much sense looking at the picture. Nothing in the picture shows us that. But if we look at our prior statements, angle 2 is congruent to angle 3, angle 3 is congruent to angle 4. We see that angle 3 is the same, so we can cut it out and just leave 2 and 4, which is what we have in step 3. So our reason here is the transitive property, cutting out the trans fat, cutting out the stuff that is the same. So far, we're halfway there. We know that angle 2 is congruent to angle 4. What we want is angle 1 congruent to angle 4. So we need to somehow get rid of angle 2 and put in angle 1. Well, none of our prior statements contain angle 1, so that's not really going to help us. Let's take it to the picture. We see angle 2 and angle 1. Well, they're vertical angles, so they're equal. So since they're equal, we should be able to substitute one for the other. So let's start with the fact that they're equal. We know that angle 1 is congruent to angle 2 because they're vertical. And since these are equal, we can plug in angle 1 for angle 2. Or in other words, we can cut out what's the same and leave that angle 1 is congruent to angle 4, which is exactly what we want. So again, we can use the transitive property to say that angle 1 is congruent to angle 4, and we have exactly what we want. So we had to use our vertical angles twice, substitute them in for each other using our transitive property to show that angle 1 is congruent to angle 4. That concludes our last example for section 2.7. Any questions, feel free to see me before or after class.